Okay, our last presentation of the day is on fire damage inspection and analysis for a pre-stressed concrete girder bridge. Our presenter is Matt Harlan. He serves as the bridge inspection and preservation practice lead for David Evans and Associates.
Thank you. Good afternoon. We have earthquake, we have impact, and then we have fire damage. All emergency response, all something that require some sort of repair versus replace decision. And so that's, preservation is obviously at the heart of that decision. But the goal here is, for this presentation, is to share some of our experience in terms of both inspection and capacity analysis of a fire damaged bridge, and a typical fire damaged bridge. This isn't like a mega fire like the scene in Atlanta maybe a year ago, but also wasn't a small fire either. Share some recommendations for you as a bridge owner in terms of when you're faced with a bridge that has had some fire damage, kind of what are your choices, and then to share a few lessons learned just from our perspective. So to do that, we'll go through, talk about some research findings, talk about the inspection that we performed, the post-damage inspection, the analysis that was performed to try and determine whatever the reduced capacity was of the damaged girders, present some conclusions, and then hopefully I'll be able to answer some questions. I would like to give credit where credit is due, though. This was a project for the city of Portland, in Portland, Oregon. Also, Amanda Blankenship, who is a senior engineer, senior team leader in our Salem, Oregon office, was the engineer of record for this project, and along with Tim Link, who's a junior engineer in our Portland office, they put together the bulk of this presentation. So the bridge in question is in, like I said, Portland, Oregon, which is, other than the WashDOT in Washington, folks, it's about as far away from here as you can get here at this conference down here in Orlando. It's a 3-span pre-stressed bulb T72s, cast-in-place concrete deck, continuous for live load, urban environment, downtown Portland, North Portland, built in 2011. This bridge has a history of homeless transient camps underneath the bridge. Both abutments, both side spans, end spans, if you will, have pretty decent size homeless camps, and you can see in the bottom photo there that was taken at the time of the post-damage inspection, when the camp basically dispersed when they had this big fire, and then immediately they were moved back in and watching intently the inspection going on across the slough. So the original bridge, so like I said, this bridge was in 2011, and it replaced, back in 2011, it replaced an existing 14-span timber bridge, steel main span, but timber approach spans, which experienced some pretty gnarly fire damage in 2009. That was where the decision to replace originally came from. This was the completed structure in 2011, like I said, pre-stressed concrete. What happened? Well, this was in 2017. A transient camp fire was started. The main fuel source of the fire was timber. The resident there had built a timber platform spanning in between the bulbs of 2 adjacent girders. If you've been around homeless camps in an inner city environment, there's always like the camp informant, the gossip king or queen of the camp, and so we ended up talking to somebody during the post-damage inspection, and so the word was that the fire was intentionally started, but we don't know that. But regardless, it was a pretty intense fire. The primary damage was in one girder bay, and this is a picture of the bay in question. This all of these spalls here, and then you've got spalls in the top of deck. This is looking sort of at the girder web and underside of top flange. This is top flange right here. And then this would be the opposite girder. You can see this real scaled profile. Pretty intense fire damage. So right after the incident, the City of Portland engineering staff went out, inspected the bridge to determine if it needed to be closed once Portland Fire and Rescue came through and cleared the site. So they determined that the damage was not extensive enough to close the bridge. They simply posted it for 25-ton single unit and 40-ton combination trucks. So no permit loads essentially. And then they came back to David Evans and Associates under an on-call that we have and said, hey, perform an inspection. Can we do a capacity analysis on this and determine if we can lift the posting or if we need to post it for lesser load. We went in and said, okay, well let's do we did the fire damage inspection, but we also said, well let's do some research because fire damage isn't something that we're exposed to quite frequently as bridge engineers, bridge inspectors, design engineers. So we said, well, let's utilize what other information is out there to help us. So interestingly enough, Amanda, who was involved in this project, and actually I failed to mention, she was also the designer, engineer of record for the bridge, for the new bridge, the bridge built in 2011 also. So she's been all over this bridge. She had also been involved in another fire damage inspection that we performed for TriMet, which is the transit agency in Portland, in and around Portland, for a structure that they had in their inventory back in 2011. So the same year that the bridge in question was constructed. This was a very similar case where you had a homeless camp, a fire ignited in between essentially one girder bay at the abutment, and you had the area, this red area was the fire damaged area. Pictures of that inspection of the localized damage. So that was the first piece of research that we did. The second piece was this incident in Tacoma. This project was actually presented back in 2004 at the International Bridge Conference, and this was a pretty huge fire. This was a tanker fire underneath a prestressed girder span. This was a hot fire. This was temperatures up to let's see, I have 30,000 gallons of methyl alcohol burned, temperatures up to 3,000 degrees Fahrenheit. Pretty intense fire. This was on the scale of an in-depth invasive post-damage inspection to, hey, let's go look at it and make sure it's okay. This was way far on the in-depth scale. They did quite a bit of destructive testing on this. They tested concrete cores. They measured deflections of exposed strands. This one had exposed mild steel and exposed pre-stressing strand to try and measure what strength loss they had in the strands. Ended up doing quite an extensive suite of testing on this. Both superstructure and substructure experienced quite a bit of damage. This is the sort of the heat map, the damage map for the fire, and you can see the railroad car tanker was basically sitting in this configuration right here. This area right here is white hot, no soot at all on the surface. And then as you go out from there, you get increasing levels of soot. So they ended up replacing this span on this bridge. It was a fairly new bridge at the time, and so the decision was made to replace the span. Third piece of research we did is a PCI document, a readily available PCI document from 1989, designed for fire resistance of precast pre-stressed concrete. I'm not going to go too in depth here, just in the interest of time, but it provides some standardized tests, estimations of internal temperatures of both concrete and steel at certain contact temperatures of fire, and then recommendations on reductions, strength reductions for given temperatures of fire. Last piece of research we did was on the rebound hammer, the Schmidt hammer. This was a really good document by CMEX in 2013 that also references the ASTM test method for the use of the Schmidt hammer. So how many, just show of hands, how many people are like experienced with the Schmidt hammer? Even more than I thought. Still, a small amount. I feel like before this project, I knew what a Schmidt hammer was, but after this project, I realized that I didn't know what a Schmidt hammer was. I'll go into that a little bit more. This is just an example of the Schmidt hammer and the testing associated with it. Big picture thoughts on the Schmidt hammer. Simplistic, pretty low impact method to get very rough indications of relative concrete strength, but I want to use the word relative. It's a great tool to be used qualitatively in comparing a damaged concrete specimen versus an undamaged concrete specimen. Without that comparison, I don't know that the numbers that you get from it are really strong and reliable. It does take time to perform because you need quite a few tests. In each test location, you need a minimum of 10 readings, and then you're averaging those readings and removing noise as well. So it does take quite a bit of time, and you want to perform as many tests as you can because you want a good profile of estimated hardness along the cross-section of the girder that then you can use correlation charts to come up with F prime C. So the inspection, kind of what we did out there in the field, we went through and took, obviously tons of pre-inspection photos. The more photos, the better with something like this. But something that really provided some added benefit was creating a grid pattern on the damaged girder because there was so much damage and so much variation in spalling depth that we went ahead and we placed out wax marker lines along the length of the affected girders, both vertical lines and horizontal lines at specific 2, 4, 6 foot intervals. This helped us correlate both our inspection notes, our photos, and then helped us actually draw up the elevations of the girders to be able to illustrate the damage a little bit more clearly, and then to be able to make more informed decisions when we're actually performing the analysis. Also looked at obvious things like concrete color, which can give you an indication once the concrete is pressure washed of how hot the fire actually got. Obviously basic sounding of the concrete to determine whether or not you had any delamination, inspection of all the cracking, mapping of all the soot and the damage as well. And then the Schmidt hammer testing. So we had a sub-consultant. We have a small women minority owned business requirement on this on-call, and this was a great opportunity to get a good qualified DBE sub that really knew Schmidt hammer testing inside and out, and so we utilized them on this project as well. So this is the plan view of the bridge, and you can see in span 1 the fire location. The red areas are the damaged areas, and then the green dots are where we perform the Schmidt hammer testing. And you'll see two little green dots over here, and those were the tests performed on the undamaged girder or the as-built girder to be able to provide the comparison. Just a more blown up view, pardon the pun, that's terrible, of span 1, and you can see the red areas where the fire was, and the relative limits of the soot mapping that we saw in the dark gray and the gray. Just a view of the underside of the bulb or bottom flange and the type of spalling that we saw there on the bottom. And photos, gonna go through quite a few photos here. You can see the span in question, and the bay that the fire was located is where the ladder is. There's photos that you saw earlier of the area where the fire was, and this is before the area was cleaned out with all the debris that was in there. So we'll go through each of the girders very quickly, though. Girders A and B that didn't have as much fire damage, although there was indication of a smaller fuel source between girders A and B, that maybe something else caught on fire and burned consistently there, because we did, on the inside face of girder A, we did have this area of spalling in the web. This is just a bottom flange spalling. This would be that inside face of girder A with quite a bit of spalling. Girder B, really not much to note here on either face of girder B. Let me go to girder C, and girder C and D were the two girders that were heavily affected with damage. You can see the length of overall spalling in the web, and then the green symbols indicate where we did the Schmidt hammer testing as well. Just a photo, you can see they've actually come back in after the fire and re-tagged the bridge. They're pretty quick. View of the underside of the bottom flange. The depth of spalling not as critical in the bottom flange as it was in the web. The max depth of spalling in the bottom flange was like a 1/2 inch. But that was in very few locations. This would be on, this is the east face of girder C, the photo that you saw before. In terms of depths of spalling here, we're talking max 5/8 to 3/4 inches. No mild reinforcing exposed in the webs, no shear stirrups exposed, no pre-stressing strands exposed in the bottom flange either. So the highest intensity of spalling in the web was between 1 and 1.5 inches, and this is girder C east face. This is right there at the fuel source. We did have exposed stirrups in this location. Bottom flange, top flange, underside, about 1/2 inch depth spalling here. Did have some hammer-induced, what we call the hammer-induced spalls, where we were sounding, and the matrix had loosened up enough and enough microcracking from like split aggregate from the fire that we did get some corner spalls around 1 inch deep, 1.5 inch tall. More photos of girder C. And you can see how well the wax marker lines helped illustrate the structure condition. Now, the opposite side in the same bay, girder D, the west face of girder D sustained quite a bit of heat damage. Good overall view. Back towards the face of the end diaphragm abutment. Out a little further, this is about, well, you can see there, 8 to 14 feet out, and then out to, say, 20 feet. Just a condition at the beam end, really lucked out at the ends of the beams. This was about the worst condition that we were seeing in the bottom flange, which was not significant. And you'll see in a few photos that the bearings actually fared fairly well. Underside of bottom flange, large spalls, and then some scattered small isolated spalling as well. So this is a map of the spalling and damage in the underside of the deck and also in the top flanges, and you can see where it's concentrated right over where the main heat source was. It's a good, just a good general view of that. We're almost at 1.5 inch depth spalling in the underside of the deck. No exposed, mild reinforcing. Did have one little corner spall in the underside of top flange that we did have some exposed mild steel reinforcing there. So this is probably the worst bearing, and it's really hard to tell there, but you're not missing anything. It actually fared really well. Elastomeric bearings held up well under heat. All the bearing markings were kind of burned off, and it had some surface scars, a little bit of deterioration along the edges of the bearings, but really no other extensive damage to the bearings. So then we did the Schmidt hammer testing as well, and that was Northwest Geotech, Northwest Testing, tested web, top flange, bottom flange, and deck to be able to compare, to develop reduced F prime C for these, for the girders, and then to be able to use that reduced compressive strength in our capacity calculations. So again, just a view of the testing locations, both in plan view and in cross-section. So originally planned to test both faces of Girder C and D. However, it became very clear once we were out there that we weren't going to have time, we weren't going to have budget to be able to do that. Kind of made a game time decision and focused on just the interior faces of girders C and D, where the main heat source was. And of course, we knew we needed to get a good girder, as built, undamaged girder and deck section. So we went out to Girder G and the underside of deck right adjacent to there to test those locations too. So many testing locations, and you really have to have the ample time to be able to do that. This is the guys in action as they're doing their tests. So we'll go real briefly into the analysis and how we developed correlations between the rebound numbers and the from the Schmidt hammer testing, and then the compressive strength. So just a summary of the procedure that we utilized. We compared. We decided the best way to go about doing this, because we had designed this bridge and we had all the capacity calculations originally, and because the bridge was designed recently for current live loads, HL93 live loads, all we really wanted to do was to get a damaged girder F prime C and develop new capacities based on that, and then look at our design ratios. Used a reduced cross-section, and we were conservative on the reduced cross-section, utilizing all of the max depth spalling along the exterior of the girder to come up with a new cross-section. And then if we're under capacity, well, then we can always sharpen the pencil. So the correlation for the Schmidt hammer numbers was the toughest part. In order to get a rebound number, you've got to average those 10 measurements, and you also have to throw out your highs and your lows, your outliers. We used the data from the previous inspection we had done in 2011 for TriMet to derive the linear relationship correlation between the rebound numbers and F prime C. We had issue getting a correlation charts for the particular Schmidt hammers that we used, and that was a struggle and maybe a lesson learned when scoping the project. We averaged all of the calculated F prime Cs for all of the test locations, and so we came up with an average worst case F prime C for shear, an average worst case F prime C for flexure, and then also for the deck. So this table is the shear. Now we also, like in a vacuum, we didn't have real good surety on those average numbers that came straight from the Schmidt hammer. So we took the Schmidt hammer results from the good girder and normalized those to the design compressive strength. So the average that we ended up coming out with for in our web readings for Girder G1, which is the undamaged girder, was 7.73 KSI when using the correlation factors. Well, we know that it's not 7.73 KSI. It was design concrete strength was 9 KSI, and we know that the QA during construction we were way higher than 9 KSI. So we actually scaled up our readings to get to 9 KSI on the undamaged girder so that we could be comparing apples to apples. Same thing with flexure, basically scaled up to get to the 9 KSI for our flexural F prime C. And then in the deck as well, we actually scaled down to get to the 4.35, which was the design compressive strength for the deck concrete. Okay. Stress checks, which I'll go into a little bit more in the conclusions. This is our section properties. Again, conservative section properties, but if we needed to sharpen the pencil, we always had the opportunity to do that. Shear, we went from a 2.12 design ratio to 1.85, so reduced capacity, but still A-okay. Moment from 1.46 down to 1.37 on our damaged girders, again, very good. And you see that those two cells in yellow, those were our stress checks for bottom fiber compression, and our applied compression, or our applied stress was higher than our allowable, so I'll talk about that. Deck capacity, we determined that really we didn't need to focus on the deck because our spalling didn't actually expose any steel, so we didn't assume any real strength loss in the deck itself, in the positive moment region of the deck. Conclusions, so we have shear strength, very adequate capacity, adequate reserve capacity. Flexural strength, adequate reserve capacity. Girder stresses. All our stress checks came out okay, except for this bottom fiber compression stress. Basically, that stress check is intended to limit creep, and which, more creep, you get undesirable deflections, you get losses in pre-stress force. We expect that the adjacent girders and deck will help restrain that, and also we were so conservative in our assumptions that we felt like this was that this stress check was okay by inspection. Repair recommendations were simply to just restore concrete cover with some basic patching, extend the service life, no real strengthening or in-depth repairs needed, and also prevention for future transient fires. Some sort of cage system prevention just from getting transients back underneath there, keep them out. So this last slide here, conclusions. Lessons learned. Number one, and this is kind of a no-brainer, consider fire protection during the design of new structures, and we do that with increased cover and with pre-stressed concrete members. Concrete is, generally performs quite well under fire. Also preventing transient access or vandalism access, if you will, underneath your bridges. Schmidt-Hammer testing can be time-consuming. It's a great qualitative tool, comparison tool, but it can be very time-consuming, and you need to account for that in your scoping. And really the big picture for this group is that the fire damage inspection, there's more than one way to skin a cat. The damage inspection can be very basic, and it can be extremely in-depth, and it all depends on the intensity of the fire and the location of where the fire was and the result on the structure. And this is a great example of kind of a project that's right in the middle of fire intensity.
The preceding was produced by the National Center for Pavement Preservation. More information can be found on the web at pavementpreservation.org. Additional support provided by Michigan State University.